Okay, remember that an eigenvector of a matrix A is a non-zero vector, so that A times x is equal to lambda times x. And this question asks, is V an eigenvector of the matrix A? And what we can ask is, okay, since A times V, and remember this would be, this matrix first, the A first, times our V, which is 1, 2, negative 1. If we do that multiplication, we get negative 1 for the first entry, then negative 2 and positive 1. And that's equal to negative 1 times our V, which equals negative 1 times V. And according to that definition, since V is non-zero, V is an eigenvector. And we would say with associated eigenvalue negative 1. Here we're given that A is a 3 by 3 matrix with the eigenvalue equal to 3, and we're asking to find the basis for the eigenspace. Remember, the way that we do that is we're looking for the solution to the equation A minus lambda I times x equals 0. So we want to find A minus lambda I, but in this case we're specified that that lambda is equal to 3. So we're looking for A minus 3I, and really what that amounts to is taking the entries on the diagonal and subtracting 3. And then we're going to set up our augmented matrix according to this equation. Put our 0 vector, and then we just reduce. Okay, and we see that we have x1 and x2 are both free variables. And if we're thinking about the solution, remember where our x vector, our unknown vector, is a 3 by 1. And so if we think about this being the augmented matrix relating to this solution, then our x1 is equal to minus 2x2 minus 3x3. So we have two free variables. That means the dimension of the eigenspace is equal to 2 because we have the two free variables. And so we're going to say x1, x2, x3 has to be of the form minus 2x2 minus 3x3, which, if we write it as a linear combination of those three variables, we get x2 times negative 2, 1, 0, plus x3 times negative 3, 0, 1. And the question is, find the basis for the eigenspace. And so the basis is the two vectors, all solutions of that form, where all solutions are linear combinations of those two vectors. So they form the basis for the eigenspace according to lambda equals 3. our method for finding eigenvalues is to find the characteristic polynomial, and the characteristic polynomial is given by the determinant of a minus lambda I, and then we set it equal to 0 and solve for the roots. All right, so the first thing we want to do is find a minus lambda I, and a minus lambda I would be negative 2 minus lambda. Basically what happens is you're just going to take the entries along the diagonal and subtract lambda on those. And then we want to find the determinant of a minus lambda I. So the determinant of this matrix, there's lots of different ways we could get it. We could just expand over the top row using our determinant cofactor expansion. And that's going to be negative 2 minus lambda, so that first entry times its minor. Right, and we've got negative lambda 0, then 0 minus 4 minus lambda. And notice that our other two entries in our cofactor expansion are going to be multiplied times 0, so blah blah blah, we don't have to worry about those. Alright, so that's good. Alright, so we end up just having to worry about this first term of our cofactor expansion, and we get negative 2 minus lambda, and then the determinant of that minor, that minor is the determinant, negative lambda times negative 4 minus lambda, and that's our characteristic polynomial. I actually, at this point, we don't have to multiply it out because we have 3 linear factors. If we set that equal to 0, then we see that our lambda, this first term is going to give us lambda equals negative 2, the second term is going to give us 0, and the third term is going to give us lambda equals negative 4. And so those are our eigenvalues for the matrix A. And notice that's always going to be a result if you check on the diagonal for an upper triangular, lower triangular, or diagonal matrix, then the diagonal values are going to give us our eigenvalues. Okay, first, this is the process of diagonalization. A is given by P times D times P inverse. So P inverse, on this one, think about the determinant is negative 1, and then we swap our diagonal entries, and then we multiply the minor diagonal entries times negative, the opposites of each other. And then since the determinant is negative 1, or 1 over negative 1, we multiply by, and we get negative 3, positive 2, and negative 1 for our P inverse. And a quick, checking that real quick, that should work nicely. Okay, so if A is equal to P times D times P inverse, then A to the fourth is equal to P times D times P inverse to the fourth, which would be something like this. And our P inverse P's are going to multiply together to give us the identity. So we end up with P times D to the fourth times P inverse. And so our P, and then our D to the fourth would be 16, 0, 0, 81. And then our D inverse, our P inverse is negative 3, 2, 2, negative 1. So it's still kind of messy to find, but we can do it. Alright, if I take the first two and multiply those two together, I get 16 here. and then 2 times 81 is 162, and 2 times 16 is 32, and then 3 times 81 is 243. So I do -3 to 2, -1, and I think that gives us 276, -130, 390, and -179. So it's just, again, it's a little shortcut for computing higher power matrices. You can't really see that much of the net effect here, but think about if you're raising to the 20th power, how it's going to cut down some of your processes.